Welcome to Module 2 on free vibration. This video will cover the fundamentals of free vibration, including definitions, types, system features, and methods for analysis. Vibration is the to and fro motion of a body, primarily caused by elastic forces. When a body is displaced from its equilibrium position, work is stored as strain energy in the elastic constraints. Key definitions include period, the time for one repetition, cycle, the motion completed in one period, and frequency, the number of cycles per second, measured in hertz. Resonance occurs when the external force frequency matches the system's natural frequency, potentially causing large and dangerous amplitudes. There are three main types of vibration. Free or natural vibration occurs after initial displacement with no external forces, maintained by inertial elastic forces. Its frequency is the natural frequency, as seen in a tuning fork. This slide reinforces the concept of free or natural vibration. After the initial impulse, the motion is sustained only by the internal inertial and elastic forces of the body. Forced vibrations happen when a body vibrates under a continuous periodic external force, such as vibrations from the rotating and reciprocating masses of IC engines. Damped vibrations involve a reduction in amplitude over time as energy dissipates, causing the body to eventually return to rest. Types of vibrations also include longitudinal vibrations. This is when a shaft elongates and shortens, moving up and down, resulting in tensile and compressive stresses within the shaft. Torsional vibrations occur when a shaft twists and untwists alternately, inducing torsional shear stresses. The particles of the body move in a circle around the shaft's axis. Vibrating systems consist of three basic elements for mathematical analysis. Inertial elements represent mass and moment of inertia. Restoring elements are represented by massless springs. Damping elements, like dampers, account for energy dissipation in the system. This diagram illustrates the basic vibrating system representation, with the inertia element M, the restoring element K, and the damping element C, subject to an external force, F of t. The degrees of freedom refers to the minimum number of independent coordinates needed to describe a vibratory system. Single degree of freedom systems, like a simple mass spring or pendulum, require only one coordinate, x or theta. 2 degree of freedom systems require 2 independent coordinates to fully describe the motion, such as x1 and x2 for the masses in a series spring system, or 2 angles for a double pendulum. Systems with distributed mass, such as a vibrating shaft, are considered to have infinite degrees of freedom, as the motion of every point on the mass must be described. The equation of motion for a vibrating system, mx double dot plus cx dot plus kx equals 0, is a fundamental expression where the terms represent damping force, spring force, and inertia force, respectively. The natural frequency of an undamped single degree of freedom system can be found using several methods: the energy method, Newton's method, the equilibrium method, and Rayleigh's method. Newton's method involves applying Newton's second law to derive the equation of motion for the system, leading to mx double dot plus kx equals 0. This method also helps derive the natural frequency and period formulas. The energy method is based on the conservation of energy in an undamped system, where the total mechanical energy, the sum of kinetic and potential energy, remains constant. Differentiating this sum with respect to displacement also yields the equation of motion. Manipulating the equation of motion allows us to introduce the natural frequency, omega n, defined as the square root of k over m. This results in a simpler second-order differential equation, whose general solution is a sinusoidal function of time. In damped free vibrations, the amplitude decreases over time until the motion is lost. The rate of decay depends on the type and amount of damping present, which can be due to fluid friction, or viscous damping, or friction between moving parts, or Coulomb damping. Viscous damping is governed by Newton's laws of viscosity, where the drag of the fluid opposes relative motion based on the velocity gradient. The damping response is categorized as overdamped, critically damped, or underdamped, depending on the fluid's properties. This image displays a free body diagram used in the analysis of a free damped longitudinal vibration system. Next, we will look at the governing equations for free damped longitudinal vibrations. Considering the equilibrium of the body, we sum the forces acting on the mass m to establish the dynamic balance of the system. This slide continues the mathematical derivation of the differential equation for the free damped longitudinal vibration system. After substitution and simplification, the governing equation for free damped vibration is obtained. The general solution to this second-order differential equation depends on the value of the damping ratio, which determines the type of system response. We are defining the variables and terms used in the solution, including the critical damping coefficient. This part details the characteristic equation obtained from the differential equation of motion. Here, the roots of the characteristic equation are derived, which are essential for determining the system's behavior. Based on the roots, 3 cases of damping are examined: overdamped, critically damped, and underdamped, each with distinct free vibration responses. The solution for the underdamped case, which is the most common in practice, exhibits oscillatory motion with decreasing amplitude. The final equation for the displacement in an underdamped system is shown, incorporating the damped natural frequency. We will now calculate the ratio of 2 successive amplitudes of vibration, which is used to quantify the damping present in a system. The logarithmic decrement, a measure of the decay rate, is derived from the ratio of successive amplitudes. This step shows the calculation of the logarithmic decrement, an important factor for characterizing damped free vibration. The final expression relates the logarithmic decrement to the damping ratio of the system, concluding our analysis of damped free vibrations.